Good morning to you. This is lecture number 22 in a new module, the fourth module of this course on advanced structural analysis. With this module we apply the matrix analysis of structures to problems with axial elements. If you see, we have finished 21 lectures, first 3 modules have been completed. The third module, which we did in the last 5 lectures, gave you the big picture view, but I am sure you would not have fully understood. That understanding will sink in as you start applying these concepts to actual problems. So in the next 3 modules, we will be applying the concepts we had broadly shown. In this particular module, we will deal with the class of structures commonly referred to as pin jointed frames. Okay? So they are usually also called trusses. You have space trusses, you have plane trusses, and you occasionally encounter situations which are one dimensional. In the one dimensional problem, you have something additional which you do not encounter in plane and space trusses in terms of loading. What could be that? No, in plane and space trusses, which are pin jointed frames, the loads are assumed to be applied always at the joints. Okay, so you have nodal loads, but in axial elements, you can have intermediate loading, you can have distributed loading. So then you have to bring in fixed end forces and so on. So we will look at that category also, which normally is not studied. So that is what we are going to do in this module. In the next module, module number 5, we will look at beams and the space structures linked with beams in a horizontal framework called grids, where you have torsion also. In the next module, we will look at the larger type of structures which involve rigid jointed plane frames and space frames. That is the most complex, and we will also include issues such as how to account for internal hinges, how to account for even axial deformations, shear deformations and so on. So we will build it up slowly. We will begin with the first level, the easiest, matrix analysis of structures with axial elements. Now axial elements can go into 1D structures, 2D structures and 3D structures. In 1D structures and 2D structures, we will demonstrate application of the conventional stiffness method, the reduced stiffness method and the flexibility method. All 3 we had covered in the third module, and we will also see how these methods can be used to space trusses, which are a little complicated, but in terms of actually solving problems, we will apply only the reduced stiffness method. So in all these elements, regardless of whether the structure is 1D, 2D or 3D, remember that element can take only axial forces, and that simplifies the analysis. In this session we will look at conventional stiffness method. All this is covered in this chapter on structures with axial elements in the book that I wrote called Advanced Structural Analysis. For a full understanding, you must necessarily refer to the book, because these subjects, these topics take time to sink in, and you need to go back and refresh your understanding. What are the type of problems that we encounter? Okay, so I will just show you 3 types of problems. This is one example of a kind of problem you will encounter with 1D systems. Okay, you can have 2 elements or 3 elements or any number of elements. You can have distributed loads, you can have intermediate loads, that is one category. Second category is a plain truss, okay. All this can be done quite easily using matrix methods, and we will demonstrate step by step. I am not asking you to write a generalized program which can be used by others, but let us just do it step by step manually. And when we encounter matrix operations such as transposition, inversion, solving simultaneous equations, we will use some standard software like MATLAB. So that is the idea, okay. We are, those of you who are having an interest in programming, you can take it a step further in your project and write programs in whichever language you wish, but that is a later step. Right now we will do manually step by step the process of matrix analysis. Finally, we look at complicated structures like this. It is a space truss, I have shown the plan and elevation, large number of elements. How to make the digital computer solve this problem is very interesting. So this is the last thing we will attempt in this module. So you have seen this picture earlier, the three types of methods that we will use, two of them are stiffness methods. We will now look at the conventional stiffness method, and later we will look at the reduced element stiffness method, and finally we will look at the flexibility method. In the conventional stiffness method, you know that we have to go through different steps when you want to program it. First you have to input the structured data, then you have to generate the element properties, then you must generate the structure stiffness matrix from the element stiffness matrices, then you must give the load input data, generate the fixed end force vector if required, then you compute the unknown displacements, you compute the member element level forces and compute the support reactions. All this can be done through matrix analysis. So now let us see how to do this. So we will go back to refreshing our understanding of how to generate the element stiffness matrix and the transformation matrix in the case of 1D, 2D and 3D axial structures using axial elements. So this is a typical picture of a 1D axial system, and an element used in a 1D axial system. You agree that there are only 2 degrees of freedom here. We have not looked at this picture in the earlier module, okay. You have 2 degrees of freedom, they are both axial degrees of freedom. The left node can move and we call that 1 star, and the right node can move, we call that 2 star. So this is the element displacement vector, this is the element force vector, right. Are they really independent, the 2 components of the vector? Speak louder, yeah.
In D, yeah.
In D they are independent, D1 star and D2 star have no relationship with each other, but F they are not, okay. Can we say something more?
They are interdependent.
They are interdependent, and actually they are equal and opposite to each other, and they are equal to the internal axial force in that member, right. Is this clear? Okay. Next we apply it to plane trusses. So this is a plane truss element. Here you have 4 degrees of freedom, we have seen this in the last module, and you are familiar with this. Here again the displacement vector has independent components, that is how we identify the degrees of freedom, but the force components are again interrelated. Can you say something about those? F2 star and F4 star are 0. Why are they 0? Yeah, so what do those force components refer to? Shear forces. So you assume that axial elements have no resistance to shear, so they are 0, and equilibrium demands that F3 star should be equal and opposite to F1 star, right. Finally we deal with the space stress element. Okay, here again you can prove that the shear components are all 0 and the axial force at the two extreme ends are equal and opposite, and that force is a single unknown. This is why the reduced element stiffness method is so easy to apply, because you do not deal with so many different quantities. You deal with one axial deformation in an element and one internal force in the element. But here this is the way it is done in the conventional stiffness method. Now let us generate quickly the stiffness matrix and the transformation matrix for these three types of elements. For this element, you know that the elongation EI is the difference between the two displacements, and it's actually, in terms of tensile elongation, it's d2 star minus d1 star. You agree? The elongation. If the elongation is known and its elastic behavior, then the axial force is related to that elongation, and that is simply the axial stiffness EA by L times the elongation, and this must be equal to the end forces. And so do you see those relationships? They are well known. One more thing, we have said that there are only two axial degrees of freedom. What about displacements within the element? Let us say the displacement at one end is d1 star, at the other end it is d2 star. At the middle of the element, what will the displacement be? 0. d1 star plus, so you can do linear interpolation, right? What is the basis for doing linear interpolation? Is it an assumption or is it exact? Can you explain further? Why not quadratic? You can still have linear elastic behavior with, so we are talking of the axial deformation u of x, axial displacement u of x.
If you take a section, then the forces will still be equal. I mean, you will have n1 of x which is still f1. So for that
we are talking of deformations, not forces.
Young's modulus is same.
N is equal to KE, so it is a linear relation.
That is talking about the overall behavior of the element. We are talking of a point, say.
Yeah, but if you take any section and find the displacement, the axial force.
That displacement we can call u of x because it is in the
Yeah,
x.
but, okay, so that will be proportional to elements.
That will be proportional. Why will it be proportional?
Because it is linear elastic.
No, that is
No.
not the answer.
It is proportional to n of x directly EI because
No,
F is
you are right, but you are not hitting the nail on the
KE
head.
of x.
Huh?
Nx is K of.
Those are all integrated over the entire length. We are now taking a section somewhere, finding how much that point moves. Okay, the clue is given in what I have shown here. I said the u is related to strain, right? The axial strain at any location is du by dx star, right? And if the axial force is constant at all values of the length, then you bring in Hooke's law, because force is directly related to stress, stress is directly related to strain. So force is directly proportional, the internal force, the axial force is directly proportional to the axial displacement. That is the relationship. Is it clear? So you will find that you have a linear variation of the displacement when you integrate it. Strain is constant, so axial displacement will vary linearly, and you can show it. For example, take this example. If you apply d1 star equal to 1, which means you push the left end by a unit quantity, you will need to apply a force, and that force will be equal to the axial stiffness. It will be positive, it will be EA by L. You will develop a reaction at the other end, equal and opposite. So K 2 star 1 star will be minus EI by L. Is this clear? This is obvious. What about the deformations? How will the axial displacement vary? It will vary like this. Okay, this is exact. You agree? I am now plotting u of x star, which means any point here I can interpolate the displacement from this end and this end. It will be maximum here and its value equal to unity because it is going to be equal to this quantity, and here I prevented the movement, so it is linear. It is linear because of this relationship and not because of any other reason. Okay, likewise if I now pull the other end and arrest the first end, I will get another set of relationships and the displacement will look like this, right. So this gives me a good picture, and this is the reason why we limit the degrees of freedom to the ends of the element, because we know everything, we know the full displacement field. And what will be the stiffness matrix here? It is a 2 by 2 matrix, the element stiffness matrix. What are its components? It is simple, it is EA by L, so there are no zeros here, it is a full matrix, but it is symmetric. All stiffness matrices are, there is no but there, all stiffness matrices are symmetric and square, no question, but there is something special about this. It is singular. Why is it singular? Yeah, that is another way of saying it's singular. She says the determinant is equal to 0. That is right. Why is the determinant equal to 0? Because the rank of the matrix is only 1. Why is the rank only 1? Because the forces are not independent. Because this element cannot resist any load unless you arrest some degree of freedom. Right? You catch hold of one end and then pull the other end, then the system is stable. So there are many ways of understanding what is mathematically apparent. Now the next question is, for such a problem, using the conventional stiffness method, you have the local axis system and you have the global axis system. Remember what we did earlier? So what will be the nature of the transformation matrix Ti? Remember Ti? It is going to be a 2 by 2 matrix. What will be the special quality about that matrix? Okay, you remember the Ti matrix? Yeah, but that is the general formula. Here in this simple example, what is the? It is an identity matrix. Why is it an identity matrix? Because x star and x are the same in this problem. Theta is 0, x star and x are the same. So these are the easiest kind of problems you will get. You do not have any inclination theta x as you would get in a truss or in a frame. So in a line element, in a system where you have line elements, the problems are very easy. Transformation matrix is always identity matrix. So it simplifies your calculations tremendously. Is it clear? Okay. Now let us look at the 4 by 4. We have done this earlier, so can I go fast on this? You know the stiffness matrix, and I think we did this in the last session, so I can. Any question on this? This is clear. But let us refresh our memory on the transformation matrix. You got a 4 by 4 stiffness matrix. In that stiffness matrix, remember there were 0 columns and 0 rows. The second and fourth rows and columns were 0 because they correspond to the shear forces. They are rigid body displacements. Okay, but in this, you remember this. Here, what is the nature of the transformation matrix? Here, you will have theta coming into play. What is it going to be? Where will you will have a negative sign somewhere, right? There you are. So these are the relationships. Okay, you will get a minus sign in this second term. We have done this, so shall I go ahead? These are the tools with which you can do matrix analysis. Once you have the tools ready, you can do it. Lastly, and this is the most difficult of the lot, if you have a 6 by 6 transformation, 6 by 6 space truss element, how do you do the transformation matrix? Hmm?
2, 3, 5, 6.
No, this is really complicated because you have an element in space, you have x, y, z and you have x star, y star, z star. So what does your direction cosine matrix look like? How many numbers do you need to deal with? Is it just theta x, theta y, theta z? No, because you need to project one on all the other three. So it's you need to know it at least in principle, because this needs a lot of thinking and clarification. I want you to read the book for this if you are interested, but to show you what you are likely, you have to use vector notation, and it works out like this. Okay, the stiffness matrix is very easy to do because you have only A by L and mostly they are full of zeros, but the transformation matrix will involve many angles, okay, x star with x, x star with y, x star with z, y star with x, y star with y, y star with z, and z star with x, z star with y, z star with. So it's a little messy, but that is why you need to program this more carefully when you do it. But this is a little advanced, and we'll keep it outside the scope of what you need to know, but in principle you should know what needs to be done. And this is where the orientation of your, let's say, eye section makes a lot of difference, whether you are pointing this way or the other way. It will all have to show up in these, because you can get everything wrong if this matrix is not well done. So this is a little tough, but you will see this reduces to such a simple thing when you do it by the reduced element stiffness method. So we will actually do problems only by the reduced element stiffness method when we deal with space frames. Is it clear? But if you want to do a generalized program which anybody can use, then you have to necessarily look into these direction cosines. Okay, theory is over. Now we get into problems, but before we do the problems, you will encounter intermediate loads in one dimensional axial system. So let us quickly finish that and then we will be ready. So let us say I have an axial element with an intermediate load P located at distance A, B, right. Now if I have a situation like this, one of the options I have is I split it into two elements. I split it into two elements, so it still becomes a nodal load, you understand, but that is extra effort. If I still want to manage with one element, then I must have an equivalent joint load. I must pass on this load P to the two ends, right. Those are the fixed end forces, if you wish. What do we mean by fixed end forces? You are familiar with fixed end moments in beam. There you arrested the rotational degrees of freedom. Here you arrest the translational degrees of freedom, and if you pull it there, you will get some reactions at these two ends. Can you guess what those reactions will be? At the left end,
BB by L.
some fraction of P will go on to the end A, some fraction will go on to the end C. Which will be more in this case if A is less than B?
Left it will be more.
Left end it will be more, right end it will be less. Will it be kind of linearly varying as you would in a simply supported beam with a concentrated load? How do you prove it? You are right, you are right. This is not statically determinate, you can't do it like in a simply supported beam. How do you prove it? Elongation, oh that is well said, elongation of AB will be equal to shortening of BC. So how does this prove you get? Okay, in terms of stiffness, which element is stiffer, AB or BC? AB, right, and the stiffnesses add up at B. You can prove it either by the force method or the displacement method. Incidentally, at the end of the last class, one of you asked the questions. Remember we tried to compare the flexibility method with the stiffness method, and the first point we wrote was what are the fundamental unknowns, and we said the fundamental unknown in the stiffness method is displacement, because the stiffness method is also called a displacement method. You have to first find displacements, okay, then only you will get, you may be interested only in the internal forces, but you can't find the internal forces until you find dA. So your fundamental unknowns are displacements in the stiffness method. In fact, there are other names for the stiffness method. Stiffness method is called displacement method. It is also called equilibrium method because you use equilibrium equations to find the unknown displacement. Likewise, the unknowns, well, everything is unknown in any of these methods, but the primary unknowns in the force method really you may not be interested in finding any displacements, but you are forced to find displacement because you have to bring in compatibility equations. So, your unknowns are redundants and the redundants are forces. Okay. So, you will find the other names for the flexibility method are force method and compatibility method, because compatibility is the governing equation. Okay, let us come back here. You can prove it, I will leave the proof to you, you guessed it correct, PB by L and PA by L. And if you want to plot the axial force distribution, as one of you rightly said, AB will go into tension, which I show positive, and BC will go into compression. So, this is what we call an axial force diagram. And if you want to plot the deflections, the displacements, how will it look? Perfect, you get a triangle and you can prove it. If you know the total stiffness of the joint, you can prove how much it will move. Why will it be a triangle? You are right. Did you guess it or?
Okay. Because B moves more.
No, now we have established a relationship.
A and C are fixed, sir.
What's the relationship we discussed a while back? It all depends on the strain. The axial displacement comes by integrating the strain, right. The strain is directly proportional to the internal force N, right. So, if the internal force is constant, the displacement will vary linearly, which is what we have done earlier. There is no shear force and bending moment here, like that, okay, like shear force and bending. Is it clear? So, that is the argument, and you can prove that it is going to be PAB by EAL. With this, you know everything about the fixed end force here. The other case you should look at is if you have a UDL, okay. If you have a UDL, what will be the reaction at the two ends? Very easy. Half of the total load P, so it is P by 2, P by 2. What will be the variation of axial force?
Linear.
Yeah, it will be linearly varying, not like the previous case. And how do you think the deflections will vary? Yeah, parabolically, and you can prove that the deflection in the middle is PL by 8A. Is this easy for you? You can also remember the formulas for deflection. That is all you need to know. Of course, you can have all kinds of intermediate loads, but let us limit to these two simple cases, store it in your memory and be ready to handle problems. There is one more type of fixed end force you can get in stiffness method due to environmental effects. So, it could be either caused by change in temperature along uniform temperature along the whole bar. You should not heat locally in one point in the bar. Let us say the entire temperature in the bar is raised by 20 degrees Celsius or cooled. So, that is delta T. So, we use the notation EI naught to refer to the change you would get under free condition, that means no restraint, and that is given by the coefficient of thermal expansion alpha times the length times the change delta T, clear? Or you could get EI naught directly in a lack of fit problem. Let us say a bar is given to be too long by 5 mm, then EI naught will be plus 5 mm, is it clear? So, here again in the primary structure, when you prevent all the movements, you will get an internal force, that will be a fixed end force, right. It is a constant force throughout the length of the member. What will it be? Axial stiffness times that. So, I hope you are familiar with this. Please remember one point, EI naught, you have to judge whether it is tension or compression and put the sign appropriately. We will demonstrate this. This slide I am going back to you do not have to mug up any formulas. Remember this playground, everything will fall in place. This is how we generate, look at this. The steps are very clear. First, identify the coordinates develop the TI matrix, develop the element Ki star matrices, do this operation first, then do this operation, put the linking coordinates and assemble your structure stiffness matrix. First assemble your matrix element wise and then assemble the structure stiffness matrix. After you solve this equation and get the unknown displacements, directly use this to get your member end forces. So let us demonstrate this with some examples. We will have time only for one example, let us look at it. This is a problem. Now I want you to actually do it with me, okay, we will work it out so that you understand. This problem, you have two intermediate loads, okay, you have two elements, you can make three elements if you wish, but that is a little extra work. You can have AB, BC and CD as three elements, in which case only in AB you have intermediate loading, but let us take advantage of the fact that we know how to deal with that 30 kilonewton load also. So we will have only two elements AB and BD, and what is the question? The question asked is, get the complete force field and displacement field, which means find out all the unknowns, find out the support reactions obviously, find out the variation in the axial force, find out the variation in the displacement. Usually that is something not done in practice, so we are interested only in the maximum displacement if at all, okay. With that you know everything. Now before we start this problem, can you predict the variation in axial force and the variation in displacement? Just scribble something in your paper, we will check out whether your intuition is right, okay, just scribble something. How will n of x vary with x and how will u of x vary with x along this full length of this non-prismatic axial system? Where do you expect there to be tension, in which section? AB will be fully under tension?
Not full in tension.
What about CD? CD is definitely in compression.
Definitely in compression.
What about BC? BC is compression. AB? Half tension, full tension? Well, there somewhere there is a transition from tension to compression. Will it exactly be at B?
No.
Could be, we do not know, because you have a constant load of 40 kilonewton acting at B. So
40 plus 30, 70, so we can't.
okay. You just sketch something and I am not going to look at it, keep it and we will check it out later. Both also draw the displacement, the u of x, okay. You can draw it separately for the three elements. Now let us proceed. How do we solve it? So first lay down the map, you help me fill up this. What is the first thing you should do? I am asking you, how will you do it using a computer, step by step? First you write down, you have to write down the degrees of freedom and label them, right? And then you should do the transformation. So this is the first step. You should identify the global coordinates, local coordinates, do the transformations and find the equivalent joint loads. All the input should be done, okay. So you need to find out the equivalent joint loads, write down your TI matrix. You can use a TI matrix to find your equivalent joint loads. This is the first step. What is the next step? Sorry? EI, there is no I here. E has no matrix, E is constant. Ki, use the right term. Element stiffness matrix and generate the structure stiffness matrix, right? You have to bring it to this form. How we do it, we will see. You can do the transformation. Now you are ready to solve the problem. What is the next step you need to do? You have got the equation, so you find the solution, find the displacements and the support reactions. You have two equations, you can solve for those two equations. you will find that in these two equations you know that there are no support movements given in this problem, so this is a null vector, this part. Take the first equation, invert your Ka matrix after you found it there, find out your equivalent loads at the active degrees of freedom, find the unknown displacements, use that to apply in the second equation and find the support reaction. Is it clear? It is very simple, very straightforward, but you have not done any problems. This is your first problem. And finally you have to find the member forces. How do you get the member forces? Well, you have first intermediate load, so you have fixed end forces, then you remember the diagonal path from the displacements, you can get the directly you can get the element level. So this is all, there is nothing more to be done. Let us do it step by step. First write down the global coordinates. Well, we are very clear there is only one degree of freedom, right? So we will label that 1. Then we have 2 restrained degrees of freedom, right? One here and one there. Let us point it all in the same x direction, we call it 2 and we put a slash to remind us that it is a restraint, and 3. Is this clear? Please do it. So you got 3. In all problems do it step by step in a simple elegant way, you will find this subject is then very easy to follow. And in the beginning make it a habit to write down neat sketches so that one look at and you will understand what is going on. Can you now attempt labeling the local coordinates? So you have to separate out the 2 elements and do the local coordinates. That will look like this, agreed? Element 1, element 2, write down the length, local x star axis, 2 degrees of freedom, 1 star, 2 star. No questions? Very clear? What is your next job? You have to do coordinate transformation. How do you move from local axis to global axis and put the linking global coordinates in brackets? Remember? Even if you do not remember, with this exercise you will understand. So I will show it to you since it is the first time. This is what we need to do and it will look like this. Remember we said the transformations are all going to be identity transformations, right? Because x and x star are aligned in the same direction, nothing to worry. So both T1 and T2 will be identity matrices, only thing you have to put the linking global coordinates here. Now you see the local coordinate for 1, left end is 1 star, right end is 2 star, but this 1 star matches with 2 global and 1 global. So that is why I wrote 2 1 2 1. In the second element 1 star 2 star matches with 1 and 3, 1 and 3, that is all you need to do. Is this clear? Is this step clear? Because this is how you link the local coordinates to the global coordinates. Ready? Shall we move on? Clear? Now you need to find the fixed end forces, okay. Can you tell me what the fixed end forces are? What are the reactions you get in the first element? What do you think this will be?
20.
Tell me the answer.
20 and 20.
20 into 2 is 40, it will be shared equally, so you get 20 20 there, and here how much of 30 will go here? 20, 2/3, right? This is 1 meter, and how much will go there? 10. And how do you label it? Well, you can write this, these are the notations we use. The first element fixed end force is written as F1 1 star F, that is this one, and this is F1 2 star F. Mind you, everything pointing in the local x star direction is positive, so they will both be written with a minus sign. You guessed 20 correctly, but you should also put the minus sign. So this, both these put together in a vector form is F1 star F. Is this notation clear to you? Can you similarly create F2 star F? What is F2 star F? Minus what? Minus 20? Minus 10, that is it. So no more explanations, you can do it. Got it? What do we do next? Well, before going ahead, let us also for our own understanding see how the axial forces and axial displacements look. Can you give it a shot? What will be the axial force variation?
Linear
Well,
increase.
it will be like this, we just discussed this, right. This UDL will give me an axial force variation linear and will give me an axial displacement parabolic, and the value of the maximum displacement here is PL by 8EA. Now here the EA is 2 EA, mind you, in this problem, so you have to write 2 times EA. EA is given as 5000 kilonewton. You get 0.001 mm, which is 1 mm. You get a 1 mm axial. This is a very small displacement, makes sense. This one, you have an intermediate load. This is the variation of an axial force. You have a triangular variation of axial deformation, and you know this is PAB by LEA. So substitute those values, you get 4 mm. Is this clear? You do not need to actually do this in most problems, but we want to have a complete understanding, so we want to know exactly what is happening in the structure. Is this clear? So this is what happens due to the fixed end force vectors. Now what do you do next? You have got this 2020 and 2010, you have to pass it on to the global coordinates. How do you do that? Yes?
It's T1 inverse.
Will you proceed? Let us see how it works out. Okay, so we are going to equivalent joint loads. What is the idea of equivalent joint loads? You want to get rid of the intermediate loads and replace it with something like this. Okay, what is the criterion by which it is really equivalent? The displacement, no, you will never get the same displacement field. No, you will never get the same displacement variation. It is the same as the displacement field, by the way. What does this equivalence guarantee? That both will have the same what? Same, no, not throughout. At B, that is all you are guaranteeing. The same displacement D1. Is it clear? That is the idea. This is the basis for equivalence. So how do you do that? Well, you do it first noting down what you have already done. You have got the two transformation matrices, you have got the fixed end force vectors. What is the transformation you do to get the fixed end forces? You are now moving from local to global. So what is the transformation you need to do? TI transpose, that is all you do. So if you look there, you have to do this. Just pre-multiply by TI transpose, which is no big deal because the transpose of an identity matrix remains an identity matrix. So the only purpose of doing this, you will end up copying the same thing, is now you are bringing in the linking coordinates. Is it clear? With the help of these two, can you identify what your fixed end force vector is? At the coordinate 1, these two will add up. That is what you are doing in the slot wise pushing, and at 2 and 3 it is known. So you can use these two and get your fixed end force vector. Does this make sense to you? That is it. Now this is what you do. Your actual problem is, you have the original nodal loads, you have now the fixed end forces which you now need to oppose, then only you will get equilibrium satisfied. So you put a minus there. These are called equivalent joint loads. This will add up to some quantity in which the first is 40. In the original load there was a 40 kilonewton, remember at B in the original problem there was a 40, that is this 40. Okay, so but you have some reactions here due to that 40 that we do not know, and then you have from this you have 40 here, so you put that 40 there with a minus sign, and you also have some reactions minus 20, minus 10, you put that there and you will get this as your final answer. This is one way of doing it, but you can do it using your own logic, you will get the answer. So let us complete this. Now you have to generate the element and structure stiffness matrices. That is easy, you know the formula. So you know that the EA by L values of each of them are known, because EA is 2 times for element 1. So is this not easy to do? This is the first one, this is EA by L, EA by L is this, and this is 1 by 3. Does it make sense? Plus 1 minus 1, so they are easy to do. Then you do the transformation, you have T1 T2, you first do, see you need to do this, but it is better to do this first, because you will need this to get the internal forces. So do this, which is actually very easy because you are multiplying with identity matrix, but now you are putting the linking coordinates, and again you multiply with T1 transpose, you will get that. So finally you have got these values. What do you do next? You have now converted the element stiffness matrix from local axis system to global axis system with the linking coordinates. You have to now put it into the slots. Remember, this matrix 2 2 will go here, you understand, 2 1 will go where, 1 2 and 2 1 will be symmetric, we can put them either way. So you have to put it in the correct boxes. Will you tell me, you do this yourself, fill up this matrix for me, this 3 by 3 matrix using these transformations, put it in the right slots. That is a little exercise you do and we will stop. You just have to add. What is K11? What is K11? Well, K11 from the first element is 1 into EA. From the second element it is 1 by 3 EA. So it adds up to 4 by 3. What is K22? K22 from the first element is 1 times EA, and from the second element there is nothing. So can you do this? It is a simple addition exercise, you will end up with this. Okay, I do not want to push you. Are you comfortable till this stage? We will pick up this solution in the next class, because you need to find the reaction. I want to do it slowly. Are you clear up to this stage, or shall we finish it straight away? Finish it, okay, good. I like that spirit. Now you have these equations, you just substitute those values, solve. How do you solve this? What is the size of your KA matrix? 3 by 3. KAA matrix, this matrix. 1, why? Because you are only one unknown active degree of freedom. So it is very easy to invert it. You solve that first equation, you will get the answer. D1 is 12 mm. Okay. After you get the answer, what do? You plug it into the second equation, find the support reactions. Okay. And if you want to interpret the support reactions, you will find that due to the joint load effects alone, you get this 80 kilonewton is passed on as 60 and 20, and due to the complete response, that is you add up these two quantities, you get 80 and 30, and you can check equilibrium, check sigma fx equals 0. Please go through this exercise, it is quite simple. What is left now? You are almost done. Yeah, you need to find the internal forces. How do you do that? Fixed end forces plus Ki Ti times D. You have to be careful about D, I will explain how. So you have the fixed end forces, you remember we calculated minus 20, minus 20, minus 20, minus 10. You have E at these two levels, but remember you have to put the linking displacements. Here you have to put D2 and D1, and here you have to put D1 and D3. That is the only thing you need to be careful about. When you do the other method, the TD method, you do not have to think, it will automatically do it. But here you have to put the correct linking values. This is the 12 mm which can be written as 60 by EA, and then when you solve it you will get these answers. Once you have got them, you have got the axial force distribution. Is this what you drew in the beginning? I asked you to guess, so you see you have to check out your intuition. You actually get 0 axial forces in the middle in this particular problem, and your deflected shape will look like this. Okay, so this is a complete solution, right? We will see how you can do the same problem using TD matrix, and the choice is left to you which way you wish to do in the next class. Thank you.